My name is Stefan Leder. I'm an application engineer with Mentor Graphics for 2.5 years now. And I would like to introduce Flotherm XT to you. I will start with a short introduction of the mechanical analysis division and then talk about the design challenges, showing a few applications and talk about where we should start with the thermal analysis. So the mechanical analysis solutions, we have our latest equipment is a 1D solution for complex systems. It's called FlowMaster, and the applications are cars, for example, the cooling systems, industries like pipe systems, and so on. Then on the component level, we have a 3D CFD solution called FlowEFD. FlowEFD is a unique tool. It's embedded into Creo, CATIA, V5, and NX. It's also available as a standalone tool, and it's a multi-purpose CFD tool. Then we have FlowVent. FlowVent is used to analyze the heat, the airflow through buildings, the contamination control, and well, HVAC in general. Then we have a hardware system. We have a hardware system called Trista. This is used to characterize the electronic parts like IGBTs, LEDs, MOSFETs. You can do thermal characterization. You can look for errors in the layers, and the good thing about that is you can do it on board. Then we have Flotherm. I think most of you will know that. It's about 25 years old. It's a clear market leader in CFD, thermal analysis of electronic systems. And from that, we go to Flotherm XT, which is actually a merger of FlowEFD and Flotherm. So let's talk about the trends in electronic. Actually, it's quite simple. Everything is getting smaller. It will have more functions. And since it gets smaller, it has a higher power density. And so we have thermal issues. So we have a range of packing requirements. This is automotive. So most electronic parts will be under the hood, which is definitely a harsh environment. So we are talking about sealed components with a high ambient temperature, with passive cooling. We have more functions, we're getting more functions, so we have to fit these additional components under the hood with a very restricted space, so we end up with complex shaped enclosures. Material constraints, of course. Cost is always a factor, the thermal performance. We have more function, a higher power density, but we can't run it at a higher temperature. And then if we run it at high temperatures, we have the thermal degradation of the components. Development constraints, well, we all need it yesterday, and we want to be the first, which means we have to reduce time to market. So the electronic design flow, where should we start with the analysis? Actually, we should start in the concept phase. The first thing we do is to analyze the thermal issues of a concept. We have in the electronic world two branches. We have the MCAD, also the mechanical part, and we have the electronic part, and they're both interacting. So we have to make sure that we do the simulation of both at the same time. Traditionally, the mechanical part is done in a CAD system. The CAD system can be, well, CATIA, ProE, whatever. But the geometries in the CAD system are made for production, not for simulation. So they are complicated. They have screws, they have gaskets, and stuff. So we have to simplify the geometry. Usually, the one doing the thermal analysis is not the one doing the mechanical design. So we have to talk to the guy doing this and tell him our needs, what he has to simplify. Same is with the EDA design. We have our EDA program, we have the export, we have IDF, we have to filter the ICs, everything what is passive and not of interest has to be removed. We have to process the layer details of the board, and then we have to define the thermal models. This all will be assembled in a CFD solver. Traditionally, then we start with meshing. Usually it's a body-fitted grid, so we mesh every surface of every component, and then we will construct the fluid domain of that. Body-fitted grid means that we have to be careful with the geometry. Usually this will be a circle where we have to go back to the native CAD system to simplify it even more, or we have to remove small gaps and translation errors for the process. Same is true for the EDA design. Maybe it's more parts than we can use for the CFD program. Then after meshing is done, we have to introduce the boundary conditions, applying power, materials, and stuff like that. Then we start solving the model. Body-fitted grids are usually unstructured, so we may have distorted cells, so we may have convergence problems, and we have to go back to the meshing, and this process can take a while. After this is done, of course, post-processing and then report generation. So this process can be time-consuming, especially the meshing part of that. Now, let me introduce you to Flotherm XT. Flotherm XT is designed to merge those two branches, the MDA and the EDA world, in one tool. It is based on a CAD kernel, so it basically gives you all the CAD functionalities if you like to, but it also have a configurable user interface, so if you don't care about the CAD side, you can just concentrate on the thermal analysis side and using smart parts and predefined geometries to set up your model. So you don't have to be a CAD expert to use that tool. We have, of course, interfaces to the EDA world. We have a FlowEDA bridge which will import all these native IDF native files from the EDA design programs like Expedition, for example. And of course, we have you will be able to use your native CAD system and then import those data. The purpose of this is to maintain a clear data consistent path from the first concept phase up to the last verification of your product. So in Flotherm XT, your analyzation process would look like this. We have the geometry, we have to assemble that. That's all the same. But we can work with native CID files. So we are able to simplify it within Flotherm XT. You don't need the interaction with the CAD system. We can filter the details at the export, or we can do it in Flotherm XT, so you have a simple model already. Native EDA files, the same. You have to import IDF files, you have to filter ICs, the layer definition, detailed models of the thermal parts, you have to apply power. But for that, we have the FlowEDA bridge, which will take care of all these steps in one interface. Then Flotherm XT is not using a body-fitted grid, but a Cartesian mesh approach with object-oriented mesh definition. So the meshing is a very short step. You can use predefined grid definition. Since it is a Cartesian mesh, it's numerical stable, and it will very fast converge. You don't have to take care of all the geometrical details. Solution, it's numerical stable, so it won't diverge, it will always converge, and the solution time is pretty short. Report generation is done automatically. You can export it to Excel if you like. The design process itself is a circle, so you start with the basic concept, then you will go back to more details. You are able to replace the IDF file, the board, for example, with a new IDF file, and FlowEDA Bridge will remember your settings. So you just import it into FlowEDA Bridge and then export it to Flotherm XT. This is just one step. You don't have to go through all the definition process again. Very time. So next thing, let me show you the process with an example. It's a wall-mounted internet box. Pretty easy model. We start at the concept phase. This can be done in using the CAD kernel, or you can use the Flotherm XT smart parts. We have predefined geometry for the components. We have predefined PCB. We have a JEDEC-based database with all the material data for the single components. Then the internet box will need an enclosure, so we add a simple enclosure. Also, this is a smart part available. For the concept phase, this is enough. It can be actually done between your first coffee and before the need of the second one. And a quick look at the results will show you that you may have a problem at this component. Now you can think about the concept to solve this. Usually this is done with a heatsink. You simply add a heatsink. You don't have to redefine your mesh because it's a Cartesian mesh and it's predefined. You just add the heatsink and start running it again. Then you can, if you want to optimize your enclosure, for example, here we just add a few holes to have an airflow through this box. Then if you run a few iterations, optimize your heatsink, you will come to a point where you think, yeah, well, this concept will work. Now, to have a consistent model, it helps if you just replace your first board with a PCB design coming from a EDA tool. You simply replace this. You don't have to do anything else. With FlowEDA Bridge, you do the definition, and you end up with this real board. Then nobody wants to have this rectangular brick on the wall, so we beautify the enclosure a bit using a native CAD system file, run a few optimizations, and then we will end up with the design we can use for our first prototype. If this is done properly, usually at least for simple problems, it will be the first and only prototype we have. So this is a very streamlined process. You can go back anytime if you like or have to, and you will end up with real data you can compare with your lab results. An application example, it's an ECU. It will have a CPU here with 6 watts. It will run in a 35-degree ambient, and we can presume that it is a harsh environment, and therefore we have to seal it using just passive cooling. So first step, we have to set up the project. We have to define the general boundary condition like ambient temperature, pressure, the fluid we are using, and this can be done in a wizard. This is all in one window. You just click through it. It helps you not to forget any important settings, and you can go back there anytime to change, for example, the ambient conditions if you want to do some what-if analysis. Then, for the first concept, we want to design a simple board, place some components where we think they are usually sitting. So we can do that using the CAD system and drawing it actually. Or if you're not that CAD-centric, you can use the predefined geometries. For example, for the heatsink, we have an extensive library where you have heat sinks predefined according to the specs of the designer, of the suppliers. And you can have small components, you can have a predefined enclosure. Then for the actual parts, we have predefined smart parts. For example, a PCB for general electronic components like heat pipes. We have, of course, fans, also based on supplier definition. We have contact resistance, for example, Bergquist bond ply. It's all based on JEDEC standard. So the point of this is that you really get to a first model very fast, and so you streamline the process. This helps you also to reduce the number of possible errors you can do. So going further, we will replace, as shown with the internet box, the board with a real IDF file coming from a designer program. In this case, it's an Expedition, using Flotherm, a Floeda bridge. From the EDA tool, we get all the material data, the power definition, the material definition of the parts. We get the definition of the layers, the placement of the thermal vias, and so on. So we end up with a pretty correct model with just a few mouse clicks. So the housing, you can also import the data, native CAD data, but you can also draw it using the CAD kernel. You can make use of all these, well, the numbers, the length and width for what-if studies, for example, more or less fins, the fin thickness, etc. You can, if you have predefined parts in your company, you can make use of the user library where you can drop all these geometries and then use them as you have to. So the mesh. The mesh is, as I already said, it's a Cartesian mesh. It's not a body-fitted mesh, so we are meshing a domain. We have three types of cells. We have fluid cells, we have solid cells, and we have cut cells, which are solid and fluid. These cut cells will represent the surface of our geometry. The beauty of this approach is that you, for example, if you're using a predefined, object-defined mesh, you can move the component and the mesh will move with it. So you don't have to do this body-fitted meshing again and again. If you simply replace this IDF file with a new one and just applying the definition of the mesh, you don't have to remesh it. Of course, there is a meshing algorithm and it will remesh it, but you don't have to waste your time on defining it. The solver, I don't know if any one of you knows FluidFD. We can automatically detect the fluid domain. If you're using an internal calculation, for example, just the internal part of the mesh, it will automatically recognize this is the fluid domain and it will shrink the overall domain to fit it. Same as actually if you are using an external, for example, you take the ambient into account, it will also recognize that there's some internal and there's some external part. You can define as many fluid regions as you wish. For example, if this one would be on the lower side water cooled, it's not a problem, you just add it. So once you have done the solving of the problem, you will have to analyze the results. In the concept phase, it might be okay just to look at the colorful pictures here, but later you would like to have detailed information of the single components. Every component in Flotherm XT is matched with a monitor point. So you will end up with a table where every component is listed, and you can see the junction temperature, the average temperature, the housing temperature, even for the passive components if they have a material attached. So this gives you a pretty good overview of the results just at one glance. You don't have to, for example, go to every single component, zoom in, look at the temperature, go out again and look for the other one. This table can use for an automatic report using Excel and then export it to, for example, PowerPoint. If you have done your first design cycle and you go back to your drawing board, for example, if you take here the heatsink, you just add a new heatsink, you don't define a new mesh, or for example, you change the material of the heatsink. It can all be done within a few mouse clicks, and it really enables you to do plenty of what-if studies in a very short time. So you reduce actually the whole design cycle to a minimum. Applications, just a short overview. For example, the first one, like a telecom router. Then, for example, a smartphone. We all know how hot our smartphone will get if we are using the GPS module and the screen at the same time. Very difficult. Then industrial automation, of course. For example, in a chemical plant, very harsh environment, sealed, most of the time passive. Computing graphic cards, they are bigger and getting hotter with the time, and especially if we start using this actually to process data other than just the optical information. And then I have seen a lot of automotive pump controllers in the last time, where you really sit on the pump in a very harsh environment, just with the passive cooling, and you try to reduce the material you are using because of the high numbers you are selling. Every cent will count. So let me sum it up. Flotherm XT is unique. It will merge the mechanical part of the design and the electronic part. It will help you to analyze the interaction between the mechanical, so the enclosure and the heat sinks, and the electronic, like CPUs and thermal vias and stuff. It also helps you to have all this data in one project. So you can go back anytime. The definition of all this data is very clean. You reduce the possibility to make errors just by translation, for example, from an IDF file to the CFD system, or from a mechanical CAD system to the CFD system.